Hello friends, myself Mr. S.K. Kulkarni, Assistant Professor, Walchand Institute of Technology, Solapur. I am here to have discussion with you on topic Interfacial Transition Zone and water requirement of concrete. The learning outcomes of the today's session are, at the end of the session, students will be able to explain significance of the interfacial transition zone in concrete and compute water requirement for concrete. Let us introduce today's topic. Dear students, to fully understand the behavior of concrete, it is important that we must first understand the structure of the hydrated cement paste. Even though it is difficult to explain the behavior of concrete fully, it is possible to explain it with better understanding of the structure of hardened cement paste. We know concrete is considered basically as a two-phase material, the paste phase and the aggregate phase. The paste phase is important as it has significant impact on behavior of concrete. Aggregate phase is also equally important. Let us see the significance of this paste phase, how important it is, on which parameters it has impact in concrete. Strength, permeability, durability, drying shrinkage, elastic properties, creep and volume change properties of concrete are greatly influenced by the paste structure. Remember, such important is this cement water paste structure. Now, what is transition zone? Dear students, if we observe at micro level, we can see that aggregate particles are dispersed in a matrix of cement paste. The complexities of the concrete begin to show up, particularly in the vicinity of large aggregate particles. And dear students, this particular area in the vicinity of the aggregates is known as the third phase of concrete and transition zone, also known as interfacial transition zone, ITZ, which represents the interfacial region between the particles of coarse aggregate and hardened cement paste. Transition zone is generally a plane of weakness and therefore has far greater influence on the mechanical behavior of concrete. In the image, you can see the area within the vicinity of the aggregate particles. This particular area surrounding aggregate particles is known as transition zone, the third phase in concrete, apart from cement phase, aggregate phase. And remember students, this is the weakest zone in concrete. Whatever cracks appear, they initiate in this particular zone and they open up after the loading is given to concrete. Although transition zone is composed of same bulk cement paste, the quality of paste in the transition zone is of poorer quality. Due to internal bleeding, what happens? The water will accumulate below the elongated, flaky and large pieces of aggregates. This reduces the bond between paste and aggregate. Remember, in the image we can see the cement paste and aggregates. The area surrounding the aggregate is known as interfacial transition zone, ITZ. And here, due to the poorer quality of paste, you will see that this is the weakest portion and the bond between paste and the aggregate is less in this particular zone. The size and concentration of crystalline compounds such as calcium hydroxide and ettringite, which is hydrous calcium aluminate sulfate mineral, are also larger in the transition zone. Such a situation accounts for the lower strength of transition zone than bulk cement paste in concrete. So we know calcium hydroxide and ettringite, these are hampering the quality of concrete or cement paste. And remember students, the initiation of cracks takes place in this transition zone only. Due to drying shrinkage or temperature variation, the transition zone develops micro cracks even before a structure is loaded. When structure is loaded and at high stress levels, these micro cracks propagate and bigger cracks are formed, resulting in failure of bond. This is very important. The initiation of cracks takes place in this particular ITZ, interfacial transition zone, and when concrete is loaded, these cracks get propagated and the cracks are widened and the concrete fails earlier. So this particular zone must be taken care of. Strength limiting phase. So it is also called strength limiting phase, this transition zone, because it is the weakest link in the chain. So it limits the strength of concrete. And because of the presence of transition zone, concrete fails at considerably lower stress level than the strength of the bulk paste or aggregate. So strength of concrete drastically reduces due to this poorer quality of paste in the transition zone. Now let us discuss the structure of the hydrated paste. We know we add water to the cement and mixing of cement paste is being carried out. In this process, what happens? Part of the mixing water occupies the gel pores and the remaining water unwanted for hydration or for filling in the gel pores causes capillary cavities. In the image we can see the gel pores and capillary cavities also. These capillary cavities may have been fully filled with water or partly with water and may be fully empty depending upon the age and the ambient temperature and humidity conditions. So this is very important that the water used is being used partly for occupying the gel pores and partly for filling the capillary cavities in concrete. Now how much water is required for this process, the hydration process? It is observed that average of 23% of water by weight of cement is required for chemical reaction with Portland cement compounds. And this 23% of water chemically combines with cement and therefore it is called bound water. Remember, this is called bound water. Now certain quantity of water is required for filling the gel pores. This water is known as gel water. How much water is required to fill the gel pores? About 15% by weight of cement is required to fill the gel pores. So total 23 plus 15 means 38% of water is required for complete hydration of cement. 38% by weight of cement, remember. So this is important. So 38% by weight of water, if we do not add, what will happen? The concrete will not be of good quality. Please assume that hydration is taking place in a sealed container. This 38% of water is assumed to be required when you are mixing cement water, right, in a sealed container, remember. The greater water above 38% will be causing undesirable capillary cavities in cement paste, which will hamper the strength of concrete. Now let us see what is the impact of water cement ratio. From the discussions which we carried out up till now, it is seen that the capillary cavities become larger with increased water cement ratio. With lower water cement ratio, the cement particles are closer together. The increase in the volume of gel due to complete hydration could fill up the space earlier occupied by water up to a water cement ratio of 0.6 or so. So up to 0.6, water cement ratio 0.6, we will observe that the hydration process takes place in a good fashion, or the increase in volume of gel which takes place due to addition of this much water will be sufficient. Otherwise, suppose water is more than 0.6, water cement ratio is more than 0.6, what will happen? The increase in the volume of hydrated product would never be sufficient to fill up the voids created by water, and such concrete will never remain as a porous mass. Let us stop this video a while and solve these review questions. Here is first question number 1. Strength limiting phase in concrete is, you have to select the correct option out of these 4. And second question is, dash dash percentage of water is by weight of cement is required for complete hydration of filling up of gel pores of cement paste. Select the correct answer from this. Okay, I hope you have written the correct answers. What is the answer of first question? Strength limiting phase in concrete is, answer B is the transition phase, is the correct option. And question number 2, 38% of water by weight of cement is required for complete hydration. So these are the correct options. Hope you have written the correct answers. These are the references for today's session. Thank you.